Welcome to the third session of the current solar panel program. In this session, you will be learning about solar panels. Solar panels, also called photovoltaic modules, are made up of individual solar cells. Each solar cell converts light into electricity and heat. When solar panels are placed in series, the voltage of the combination of the panels will increase. Solar panels in series is called a string. When multiple strings are placed in parallel with each other, you create an array. An array is used to increase the current output. In order for electricity to be generated, solar cells must be able to efficiently use the photoelectric effect. In 1921, Albert Einstein was awarded the Nobel Prize in Physics for the photoelectric effect. This is the ability for materials to emit electrons when in contact with light. When certain materials are bombarded by light, the loose electrons are given kinetic energy and jump off of the material. Kinetic energy can be calculated as half the mass multiplied by the velocity squared. The higher the amplitude of the light wave, the more kinetic energy the electrons will have. Think of this interaction as waves of different height hitting beach balls off of a dock. The higher the wave, the faster the beach balls will move. A solar cell is made up of multiple layers of material. On the top is a glass cover and anti-reflective coating to protect the cell from damage. Behind the cover is the front contact grid used as the negative terminal of the circuit. Next is the N-type silicon, which is a type of semiconductor with excess electrons. Under this layer is the P-type semiconductor, which contains free holes, or an absence of electrons. Lastly, the bottom layer is the back contact, which is used as the positive terminal of the circuit. When the sunlight hits the solar cell, the excess electrons in the N-type layer are emitted, and they travel to the P-type layer. Due to this action, an electric field forms within the cell, creating a current. There are three main factors that play a role in determining how much power a solar panel will generate. These include temperature, amount of sunlight, and load resistance. We will first discuss temperature. Looking at the graph on the left, you can see the power is greatest with colder temperatures. For the other two, let's look at the graph on the right. As you can see, there is a specific voltage and current that generates the most power. The current depends mainly on how much light is hitting the solar panel, and thus, if the sunlight is constant, it should remain close to the same. Voltage, however, depends on the load resistance and temperature. The load resistance is essentially the total resistance of the components in the connected circuit. In order to generate the most power, a solar panel should be at low temperatures, in direct sunlight, and should have an appropriate load resistance. In this activity, you will attempt to find the max power point of your solar panel. The circuit on the left is the one you will be building. You will use a multimeter to measure and record the current and voltage for the different resistor values. Each resistor will be a new point on your graph. The multimeter has a positive red prong and a negative black prong. To measure voltage, you will want to connect the multimeter in parallel with the load resistor. That is, connect the red prong to this red dot, and the black prong to this black dot. To measure current, the multimeter has to be in series with the resistive load. Connect the red prong to the red dot, and the black prong to this new black dot. Here are some more detailed diagrams with information about how to use the multimeter to measure current and voltage. Also, make sure you have the multimeter set to the correct setting, current or voltage, when you try to take a measurement. So, for each of the 5 resistor values, build the above circuits and measure the current and voltage generated by the solar panel. Then use the equation power equals current times voltage to calculate the power. Lastly, draw a graph with power generated on the y-axis and voltage on the x-axis. Alright, so now we'll be demonstrating activity 3.1. The point of this activity is to test our solar panel out with different resistor values to see if we can find the maximum power operating point for this particular solar panel. So we're going to be hooking up the solar panel to different resistors and measuring the voltage and the current that the solar panel generates. So for this activity, you're going to need, obviously, a solar panel, a 47 ohm resistor, a 180 ohm resistor, and also a 1K, 10K, and 100K ohm resistors. You'll also need a couple alligator wires, some various jumper wires, a breadboard, a digital multimeter that measures both voltage and current, and some kind of calculator. let's get started. All right, so the first thing we're gonna have to do is modify the solar panel that we have a little bit. So you see the solar panel comes with a barrel jack power cord. We actually need to cut off the end of this so that we can expose the leads underneath. And that's what I've done here. So I've just soldered some wires so they're a little bit easier to plug into our breadboard. So the first thing we're going to do is just hook up this solar panel to the 470 ohm resistor. So we're going to use our breadboard here. I'm just going to connect this right here. And then we're going to take the positive end of the solar panel, which is this red wire, and connect it to the one end of the resistor and the negative end to the other side of the resistor. Now, when we're measuring voltage, we have to measure it in parallel to the resistor. So I'm going to use these other jumper wires here and just attach them to the ends of the resistor as well. And now we can use our alligator wires to connect our multimeter to these two ends of the resistor. So we're going to take the negative end and connect it to the negative side. And then we'll take the positive lead of the multimeter and we will connect it to the positive side of the resistor. And as you can see, our multimeter is giving us some kind of voltage. So here it looks like it's, if I block the solar panel, it decreases, and if I let light shine on it, it increases. So it looks like, if I don't move at all, we have a reading of somewhere around 66 millivolts. So we're going to record that value. So this is for the 47 ohm resistor. And our power here, we're going to calculate in a second. Our voltage is 66 millivolts, which is 0.066 volts. And now we have to measure the current as well. Now current is going to be measured a little bit differently. So we have to measure current in series with the resistor instead of in parallel. So we're going to be using our multimeter to basically complete the circuit. So I'm going to disconnect the negative side of our solar panel. And I'm going to add the positive end of our multimeter on the other side of the resistor and the negative side of our multimeter to the negative side of the solar panel. Now we can go ahead and reconnect everything. Connect this here and then this to right here. And we're going to change the reading on our multimeter to amps. So now here we're getting a reading of about 1.3 milliamps. So we're going to record that. And now we're going to calculate the power. Now, as you remember, power is equal to voltage times current. So we're just going to use a calculator to multiply 0.066 times 1.3 milliamps, and we get a reading of 0.086 milliwatts. So pretty low, but again, this is a very small solar panel, so we don't expect much. Now we're going to repeat this process with the 180 ohm resistor. So we can go ahead and measure current first since we have that already set up. And we'll just replace the other resistor with this one. Now if I move away from the solar panel, you can see it steadies itself at around 1.35 milliamps. And then we'll again rearrange this so we can measure the voltage as well. So I'm going to disconnect the ends of the multimeter, put this back to the other side of the resistor, and then again we have to connect our multimeter in parallel when measuring voltage. I'm going to connect that, and then we'll connect this to this side. And if I move away, we see we have a reading of about going got to move this back to voltage. So as we can see, it looks like we're getting something that's greater than 200 millivolts. So as you can see, we're getting something that is somewhere around 0.22 volts. Oops, sorry. 2 volts. Now again, we're going to calculate power by multiplying the voltage and current together. So 0.22 volts times 1.35 milliamps gives us a power of 0.0, oh sorry, this is just 0.297 milliwatts. Now with these power readings we've just gotten, we're going to plot them on a voltage versus power graph. So for our 47 ohm resistor, we have a voltage of about 0.066, so very small. And our power is somewhere around 0.086. So there's one of our data points. Then for the next resistor, we have a voltage of 0.22 volts, which is going to be much farther over here. And then a power of 0.297 milliwatts, which is going to be much higher. So we're going to just repeat this process for the remaining 3 resistors and see what our voltage versus power graph looks like. Here are the results I got when completing this activity. As you can see, the resulting graph resembled the curve we saw earlier, where we have a point at which the solar panel generates the maximum amount of power, and then the power generation drops steeply. From this, it looks like the max generation point of this solar panel occurs with a resistance of 1000 ohms. During this session's construction, you will be creating a stand for the solar panel and attaching it to the case. In addition, you will be wiring the solar panel to your circuit. Here are the tasks you need to do to complete this session's construction. Alright, so now I'll be demonstrating the second construction for our solar panel device. So for this construction, we're going to be taking our solar panel that we've just tested out, and we're going to be attaching it to our solar panel device as we've built it in the last session. So for this, you're going to need the box that you've been working on for the last session. You're going to need the solar panel, a small sheet of some kind of metal. We use galvanized steel, just something you can bend and it'll hold its shape, and some kind of tape or adhesive strips. Let's get started. Alright, so the first thing we're going to do is just take the box and we're going to remove the cover so that we can access what's inside. Now, we're going to just be taking this circuit that we built in the last session, and if you recall, we had a battery hooked up to this so we could test it out. But now what we're going to be doing, instead of a battery, we're going to be attaching our solar panel, basically exactly where the battery was previously. Now we want to be careful because we want to basically feed the leads of the solar panel through this hole. So we don't want to attach it before we do that. So the first thing we're going to do is go ahead and feed these through this hole. We can just kind of pull them through. If the hole's not big enough, you can just pull them through one at a time, and then you should be able to get them. There we go. So now that we have that in here, we can hook up the solar panel to our current sensor. So the positive end of the solar panel is going to be connected to the VIN plus pin of the current sensor, and the negative end of the solar panel is going to be connected to ground. And as you can see, the LED lights up. That indicates that we've hooked up everything correctly. And a further test can be if we cover the solar panel, you can see the LED dims and brightens if I remove my hand. So we know that everything has been wired together and is working properly. So now the next thing we're going to do is take our sheet of galvanized steel and we're going to just bend it into a 45-degree V shape. So something approximately like that. And we're going to be taking this and attaching it to the top of our case. So we can go ahead and put the cover back on. And then we want to take our adhesive strips or tape or whatever you're using, and we're going to attach 2 to the bottom side of our solar panel, or sorry, of our metal. and then we're going to stick this to the top here. You can make sure it's tightly on there. And then we're going to be taking our other adhesive strips and attaching them to the other side. These are going to be used to attach our solar panel. So we can go ahead and take our solar panel and just stick this approximately centered on the metal sheet. And just make sure that you stick that on as well as possible. And that is construction 2 of our solar panel device. Now we will talk about the main experiment for this program. The main goal is to determine which cardinal direction will enable a solar panel to best fit the demand for power on the power grid. Most solar panels on houses send their energy to the electric company first in order to gain some additional money and other benefits, because it can be sent to other people on the grid. The last session will include looking at data, but for now you will complete the first page of the experimental method handout provided to you. Brainstorm some ideas regarding which direction you think would be the best, and think about information you already know about the sun and the demands of the power grid. This concludes Session 3 of the current solar panel program. I will leave you with this quote: "We cannot solve our problems with the same thinking that we used when we created them."